circulation can also be called abyssal circulation, which is the simple model that we just described. But now what we really talk about is meridional overturning circulation. Which is the same as the thermodynamic circulation, so there is diffusion, but there is also wind stress, and that the wind also upwells deep waters. Okay, so wind stress will also be important in the upwelling part. I don't know why you cannot see this. It doesn't fit. Okay, wind stress will have to be important. So this is a map that we saw a few weeks ago. These yellow dots are the source points. Okay. The red arrow will be the interior transport that returns at the surface the overturning cell. And the blue is the deep western boundary current. Now you know why it's in the west. Okay? And you know that the strength of this deep western boundary current is twice the source, because it's the source at the north is the source plus the transport given by the interior transport, which is equal to the source. And this is to a certain extent upwell to the surface, but most of this deep western boundary current crosses the equator and reaches the Southern Ocean, okay, and then travels everywhere. And there's a lot of upwelling, wind-driven upwelling in the Southern Ocean that closes this overturning. Okay. You need this wind-driven upwelling in the Southern Hemisphere to close the loop. There is a lot of diffusion. You see these red dots, mix-driven upwelling. There's a lot of diffusion, but it's not enough to close the circulation. Okay. So these are the main ingredients of what we've been talking about so far. The gyres, we know the theories of the gyres. The depth of the gyres is given by that scaling that we saw today. And below the gyres we have, for example, this upper cell with a source here, some mixing but not enough, and a lot of upwelling at the Southern Hemisphere, where you have the strong winds blowing from west to east out of the board, generating this Ekman transport towards the equator and a strong upwelling, closing the loop. Okay, so the sources, these sources region, we put one here in the North Atlantic, we can put another one close to Antarctica. So the sources of deep water are basically located, this graph, is instead of south-north, it's north-south, but anyway. So you generate deep water in the North Atlantic and you generate deep water close to Antarctica, mainly through brine rejection. So you form sea ice, water around you becomes saltier, denser, and sinks to the bottom. The water that you generate in Antarctica is denser because of brine rejection, larger brine rejection, and cold is denser and actually fills the abyss below the water produced in the Atlantic, which is dense but not as dense as the one produced in Antarctica. Here you have the wind-driven gyres to a certain depth, which is given by the influence of the wind stress. These are the main regions of deep convection and brine rejection, these source sites. Okay. There are two in the North Atlantic, Labrador Sea and the North Sea. There's actually a deep convection site in the Mediterranean as well, when you have strong events of winds in the Gulf of Lion, south of France. And more deep convection south in the Southern Ocean, close to Antarctica, okay, where water gets particularly cold and particularly salty, and you generate convection, okay, where you generate this Antarctic bottom water that is very dense and fills the abyss. this. So the abyssal circulation that we saw today was this very simple way of looking at the problem. Cooling source region by hydrostasy, a pressure gradient that moves the water towards the equator. Diffusion that goes back to the surface. Positive vertical velocity, therefore a geostrophic current towards the north. Okay. And closing this. This is the simple way in a advection diffusion system. So this is just a conservation of potential vorticity. Remember we saw the vertical velocity in the Svergiu balance, vertical velocity is positive, so meridional velocity has to be positive. You can think about this as conservation of PV. You have a localized sinking somewhere and a widespread distributed upwelling of vertical velocity positive. So you can also think that if vertical velocity is positive, that is stretching the column of water. So is moving the column of water upwards. So H increases. If H increases, F has to increase in order to conserve PV. And so is moving towards the north. Okay. So that's a conservation of PV, which is this very balance. And that is the interior transport. And so we saw this simple model of the abyssal circulation, which is actually called Stommel and Aron's model. So what about the upwelling part of this meridional Bertonian circulation? So you need diffusion to return the convected waters back to the surface. And so you can argue, like in this case, that diapiconal diffusivity governs the strength of the overturn instead of the convection side. Okay, so if you think that vertical diffusivity is the only reason why you close the cell, instead of saying I produce this much of source water and then I need to close the cell, you can make your argument the other way around. I have this much vertical diffusivity in the ocean, so I upwell this much water that I will need to sink somewhere else. So vertical diffusivity can also govern the strength of your meridional Bertonian circulation. So you produce a certain amount of water that is determined by the vertical diffusivity in the ocean. And that is actually how you play if you're an ocean modeler and in the model you don't have a very strong deep water production for whatever reason in your model. You cannot change your buoyancy fluxes because those are given by the atmosphere. So what do? You increase or decrease vertical diffusivity in the ocean. So if you increase vertical diffusivity, you upwell more water, and so you sink more water somewhere else. We can put this. So, okay, let's talk about this. So, how do you generate that very dense water close to Antarctica? Is through Brownian rejection, as I said. So how does it work? If this is Antarctica, okay, you have very strong winds that are actually called katabatic winds blowing from the continent into the sea. So these cold winds, they blow the sea ice because you think, okay, I form sea ice, the sea ice is there, spreads salinity around you, and I form deep water, and that's it. That's the end of the story. But actually there are cold winds that blow the sea ice away from the continent. Okay? And so if you blow the sea ice away from the continent, then the surface ocean is again in contact with the atmosphere, and you can form more sea ice. And so you expel more salinity around you, and you form more bottom water. Then the sea ice is blown again out into the sea, and you can form more sea ice. So you continuously form sea ice, and you continuously produce Antarctic bottom water. Okay, so this is another one of the famous schematics of the meridional return circulation or the conveyor belt. So how long does it take to complete a full circuit? Because some water is upwelled by diffusivity here, some water is upwelled by wind-driven upwelling in the Southern Ocean, but some water actually goes into the Indian Ocean and then is upwelled by diffusivity. Some other water travels along Antarctica and is upwelled into the Pacific Ocean by diffusivity, and then becomes the surface branch of the meridional return circulation and returns into the North Atlantic. So not all of the water is upwelled by diffusivity in the Atlantic, and we know that is not enough. But not all of the water is upwelled by wind-driven upwelling in the Southern Ocean. Most of it, but not all of it. And some goes into the Indian Ocean, into the Pacific Ocean. So if you follow a parcel of water that is sinking in the North Atlantic, here in the source region, and is not upwelled by diffusivity, and is not upwelled by Ekman pumping, but actually goes around into the Pacific, then is upwelled by diffusivity, and goes back to the North Atlantic, how much does it take? How much does it take to make a full circuit? It takes a long time. So remember we looked at the example of oxygen concentration in the ocean, in the, yes, at a certain isopycnal level, which was at the bottom. And we saw that it was flowing as a deep western boundary current. You can look at another proxy for the ocean, which is carbon-14. Okay? So carbon-14 decays very slowly. Decays every 5,700 years or so. So you can measure how much carbon-14 is in your parcel of water that is given by the atmosphere at the surface, and then you can track that parcel of water by its concentration in carbon-14. So a lot of carbon-14 means that water was at the surface recently, okay, in contact with the atmosphere, getting carbon-14. Less carbon-14 means that the water was at the surface less recently. So it has been traveling some time, and it was not in contact with the atmosphere with some time. So, what is this representing? Approximate content of carbon-14 of the atmosphere now is that 100%. So you can start with a parcel of water at the surface has 100% of concentration of carbon-14, equivalent to the carbon-14 of the atmosphere. Then it sinks to the bottom and it starts traveling, and it will have less and less carbon-14 as a percentage of the amount at the surface. So you can get a map of that. And so less carbon-14 means older water that was in contact with the atmosphere a long time ago. Okay? This is annoying. Can I move this? Okay, so a lot of carbon-14, in this case, is red. And so you have a lot of carbon-14 in the North Atlantic, where the water was recently in contact with the atmosphere. And then it's sinking to the bottom recently with all of its carbon-14 concentration. And then it starts traveling and it starts losing its carbon-14. And the pink or blue color means less carbon-14. This, I think, is in percentages. Percentage deviation from the surface. So the oldest water, so less carbon-14 means very old. The oldest water means Pacific, okay? Because you are in contact with the atmosphere in the North Atlantic and in the Southern Ocean. Then you sink to the bottom and you start traveling. And the longest route is all the way to the Southern Ocean, traveling and then filling the Pacific, and then being diffused to the surface. So here we are at the bottom, and the oldest water is here in the North Pacific. and this water sunk in the North Atlantic. Okay? So this means very old water with less carbon-14. And so from this you can, from the percentage of carbon-14, you can estimate a time scale of the deep circulation. And if you take these numbers of percentage, is about 1,000 years. Okay? Is it? Oh, okay, so a typical time scale of a full circuit for the full meridional return circulation is about 1,000 years. Okay? And you can get this by the concentration of carbon-14, for example, which decays very slowly, so you can follow the concentration of this water. So 1,000 years is a lot, and so what this can mean is that if you make any change to the surface of the ocean or the atmosphere that is in contact with the surface of the ocean, for example in the North Atlantic, so for example you put a lot of CO2 in the atmosphere, an excess heat into the atmosphere, and then the ocean, instead of thinking about the carbon-14, the ocean takes that extra CO2, anthropogenic CO2, with it and sinks to the bottom and then starts recirculating. So it will take that information of excess heat or excess of CO2 all the way to the Pacific and then back, and it will take 1,000 years to recirculate that information. So it will adjust on these kind of time scales. So even if we stop now emitting CO2 into the atmosphere, the ocean is traveling. Imagine those particles or parcels of seawater that are traveling right now at the bottom of the ocean with those information of extra CO2 and excess heat that we have put in the atmosphere. So even if we stop now doing anything, emitting CO2, polluting and everything, it will take centuries for the ocean to adjust to what we have done so far. That's why the sea level is rising, but sea level will not stop rising even if we stop emitting CO2 now or polluting or putting excess heat into the atmosphere. Because even if we stop now with emissions of anthropogenic CO2, the ocean will adjust in centuries, and so the sea level will keep rising for centuries. Okay? So the question is how much we want the sea level to rise. So when do we want to stop emitting CO2 and reduce the slope in sea level rise? But sea level rise will continue to rise for a long time because it's a long adjustment process. And so, in case you've noticed, the Southern Ocean has an important role in all of this global meridional return circulation because it can upwell all of the water that was not upwelled to the surface by vertical diffusivity. So it's important because of the Ekman pumping, wind-driven upwelling in the Southern Ocean to close the meridional return circulation. If you think about the Atlantic Ocean, but if you think about the global meridional return circulation, as you saw, the water that is not upwell in the Southern Ocean travels along Antarctica and goes into the Indian Ocean and into the Pacific Ocean. So Antarctica or the Southern Ocean has a pivotal role in redistributing whatever information, for example, in the North Atlantic you put, then is redistributed into the Indian Ocean, Pacific Ocean, and around and going back into the Atlantic Ocean through the Southern Ocean, which is like here is depicted like a cylinder that is rotating, right? And the water that is sinking in the North Atlantic goes into the Southern Ocean. It can upwell and close the cell within the Atlantic Ocean, or it can circulate and go into the Atlantic Ocean or into the Pacific Ocean. Okay? So the Southern Ocean is very important for this because it's redistributing all of these water masses. Some of these water masses are upwelling along Antarctica, and some are just going into the different ocean basins. And the dynamics of the Southern Ocean is actually quite interesting and difficult, okay? Because if this is the north and this is the south, here you have the Antarctic circumpolar current that is mainly driven by the wind stress that is blowing from west to east, so out of the board. And here we have the simple Stommel-Arons model with diapicnal diffusivity. But actually the diapicnal diffusivity is not enough, so a lot of source water that we now can call North Atlantic deep water is upwelling in the Southern Ocean by Ekman upwelling. And then it closes the loop. Some other water is formed here is the Antarctic bottom water by Brown rejection, is forming Antarctic bottom water and is recirculating into the Atlantic Ocean, into the Pacific Ocean, into the Indian Ocean. And that is also closed, this cell is also closed in the latitudes of the Antarctic circumpolar current by Ekman upwelling. So this water is coming back to the surface also by Ekman upwelling and is closing the circulation. So what is happening here in the Southern Ocean is that you have warming and cooling, and that tilts the isopycnals, but also a lot of wind stress that generates the Ekman pumping that tilts the isopycnals anymore. And so this North Atlantic deep water rises back to the surface following isopycnals, so it doesn't need diapycnal diffusivity. It doesn't need this, I don't have it here, that kappa V to upwell the water across the isopycnals. Okay? You can close this loop here without diffusivity, because this North Atlantic deep water is, this is north and this is south. Okay? We have sinking of water, and then we have isopycnals. In the limit of vertical diffusivity going to 0, then this water that was produced in the source region is flowing along isopycnals. So diapycnal diffusivity is equal to 0. And all this water is flowing along the isopycnals. How does it go back to the surface if diapycnal diffusivity is equal to 0? It's because in the Southern Ocean, isopycnals are tilted towards the surface because of Ekman pumping. You have wind stress, strong wind stress, this direction out of the board, that generates Ekman transport. We are in the southern hemisphere, so towards the left. And that rises the isopycnals, okay, because of Ekman pumping. And so now the water can follow the isopycnals and go back to the surface. And so you can close the circulation even in the limit of very small vertical diffusivity. Okay, so a lot of schematics. So what is the meridional returning circulation that we know so far? A simple schematic of what is happening in the Atlantic Ocean. You have deep water production, the source site, North Atlantic deep water through hydrostasy flows towards the equator. There is some diapycnal diffusivity into the thermocline, into the upper layer, but not that much. Most of this flows along the isopycnals and then is upwelled in the region of southern hemisphere where you have strong Ekman. So mixing driven upwelling is these red arrows. There is some, but not enough. And well, the rest is what we know. Okay. You can have two cases, so I just show you the case of vertical diffusivity going towards 0. You can have a different case of wind going to 0. Okay. This is no wind, what we looked at before. Okay, there's no wind, so the only way you can bring water back is to mix it. And this second case is where we do have wind and no vertical diffusivity. So the water sinks, flows along the same isopycnals and then is going back to the surface. You need some vertical, you need some diapycnal diffusivity, because at some point you have to cross this isopycnal. So it cannot be isopycnal, the transport cannot be isopycnal at the surface. At some point you have to cross. And so the most probable case of the meridional return circulation in reality is a mixture of the two. So you need some vertical diffusivity, but somewhere, not everywhere. Like in the case of the western boundary current, you need diffusivity to cross f over h contours, but then you can just flow along f over h contours without diffusivity. Same thing for the meridional return circulation. You can sink water and you can flow along isopycnals without vertical diffusivity. You can have some vertical diffusivity in some places, but you can rise to the surface along isopycnals and then cross isopycnals with some vertical diffusivity. And actually observations are telling us that vertical diffusivity is very small generally in the ocean. Okay? So that estimation by Munk of 10 to the minus 4 is wrong. So vertical diffusivity generally is very small within the interior of the ocean, but it's actually very large where at the bottom and along the boundaries, where you have interaction with the boundaries, lateral boundaries and the bottom. So their vertical diffusivity is very large. But in the interior of the ocean is much smaller than the predicted by Munk. So you have diffusivity but localized. So the picture that you should have in mind of the meridional returning circulation is something like this. Sinking, flowing along isopycnals, some mixing-driven diffusivity or diapycnal diffusivity, okay? But most of this is upwelling along isopycnals in the southern hemisphere region. And the bottom cell will be this, by generation of Antarctic bottom water and recirculate. Some isopycnal, some diapycnal diffusivity between the two, but most of these two cells are closed in the Southern Ocean by Ekman upwelling. In a model, if you turn off the wind and you leave vertical diffusivity, the MOC cannot be sustained. Okay, you need the wind stress and the Ekman pumping in the Southern Ocean to close these two cells. If you do the opposite, you reduce vertical diffusivity by a very, very small number and you keep the wind stress, the meridional return circulation is reduced, but you can maintain a stable meridional return circulation. So winds are more important than diapycnal diffusivity globally. In some places, diapycnal diffusivity is much more important than wind, of course, but in a global sense, wind is a major player. Okay, so for the MOC, what you need is wind stress in the Southern Ocean, that it doesn't appear, but it's a tau, diapycnal diffusivity, and buoyancy fluxes of the surface. Okay, buoyancy fluxes of the surface will give you the meridional gradient in buoyancy fluxes, generating this source of mass in the polar regions, and then wind stress and diapycnal diffusivity. That is supposed to be a tau. Okay, so that was, I need to write the notes about this, but this is the main conclusion of this is that this model is very nice, but is not enough to explain the present-day meridional returning circulation. You need the wind stress to close the circulation. Okay. So we could stop here, or we could talk about the ocean heat transport. I don't know. Did you talk about heat balance in the first part of the course, surface heat fluxes, and heat transport? Did you? Well, let's see how much information do I have. Okay, well, we can talk about this. It's just a few slides. So the ocean heat transfer. So you have a clear picture, well, clear. you have a picture of the meridional returning circulation in the ocean. How do you drive the meridional returning circulation at the surface, and how do you close the cell by diapical diffusivity, but mainly by wind stress in the Southern Ocean. Okay? So that's why I was saying at the beginning that wind-driven gyres are wind-driven. Okay? Below certain depth that we call D, the ocean doesn't feel the wind stress, and so it's not driven by the wind stress. And we had this abyssal circulation model. But actually, even the abyssal circulation is somehow driven by the winds, because in reality, you can close this abyssal circulation by wind stress in the Southern Ocean. Only vertical diffusivity is not enough. So even the abyssal circulation is somehow driven by the wind stress, not directly, but indirectly. So you have this large-scale meridional returning circulation, and you can talk about many things about this meridional returning circulation, the stability, and the importance in redistributing mass. But one of the major key, I think, is ocean heat transport. Right? So this meridional returning circulation is not only transporting mass or volume, but is also transporting heat or energy. That's why the Atlantic Ocean is so important in redistributing heat. So if you start by and having in mind climate change, perhaps, right? This is a complicated but very interesting map of the Earth's heat budget. Okay. So I have. Sorry. Incoming solar radiation is roughly 340 watts per meter squared. Okay. Some of this is reflected by clouds, some of this is absorbed by the atmosphere, some is emitted by the atmosphere as outgoing long-wave radiation. You can look at all the numbers. Presently, it should be imbalanced, okay? How much energy is coming in, how much is reflected by the atmosphere, how much is getting reflected by the surface. Presently, we are imbalanced, okay, because we are emitting CO2, producing an excess heat, and so the present imbalance is about 1 watt per meter squared. Okay, so that's how much extra heat we are putting mainly into the ocean. Of all the insolation, of all the energy, about 20% is reaching the Earth. The rest is reflected by clouds, absorbed, and about 50% is absorbed by the ocean and the land. Land is a tiny fraction of this, so most of it, about 50%, is absorbed by the ocean. Okay? So the ocean absorbs a lot of heat or energy that is coming into the system. So why is the ocean so important in terms of energy budgets in the climate system? And if you think about climate change, if you put this extra 1 watt per meter squared into the climate system, most of it will go into the ocean. Okay? So that's why the ocean is so important. And you can think about this looking at the heat capacity. Right? The heat capacity of the ocean is about 1,000 times larger than that of the atmosphere. So in the top 3.5 meters of the ocean, you have as much energy as the whole air in the planet. Okay? So 3.5 meters of the ocean, they have as much energy as the whole column of the atmosphere globally, because of the much larger heat capacity of the ocean. So that's why the ocean is the largest reservoir of heat in the climate system, naturally. But also thinking about climate change, most of the heat we are emitting into the atmosphere cannot hold the extra energy. Okay? Some of that heat will go into the land, but a tiny fraction. Most of it will go into the ocean because of its larger heat capacity. So that's why the ocean is so important in terms of climate change and extra heat. Okay? Where is that heat going into the ocean? You might have seen this surface heat flux map before. Most of the heat is going to the ocean in the equatorial regions, of course, because of insolation. Okay? And so red to yellow means heat into the ocean, and blue means heat out of the ocean. Okay? So there's a lot of heat entering the ocean in the equatorial regions and heat going out of the ocean in the polar regions, where the ocean is relatively colder. Okay? You have a lot of heat loss in western boundary currents because they are very warm, much warmer than the atmosphere above, so the heat flux is out of the ocean. So you can see here already that there is going to be a redistribution of heat that is getting into the ocean, heat getting into the ocean in the equatorial region and out of the ocean in the polar region. So if there's a gradient in this heat, there must be some meridional redistribution of heat going on. Okay. You can divide your heat fluxes into long wave, sensible heat flux, and latent heat flux, and these are the usual time mean and zonal mean profiles. But what I wanted to say is so most of the incoming radiation occurs in the tropical and equatorial regions, of course. And there is more incoming radiation than outgoing at latitudes poleward of 35, so there's more heat going into the ocean than out in equatorial regions. And there is more outgoing radiation than incoming in the subpolar regions. So there is a net gain in the equatorial regions and a net loss in the polar region. Okay? So in order to maintain a heat budget at every latitude, the ocean, and also is the same thing as for the atmosphere, they must transport heat poleward, so from the excess heat at the equator towards the polar regions where you have the deficit. Okay. And so you have meridional transport of heat. So in the equatorial regions you have more heat getting in than out, and in the polar regions you have more heat getting out than in. So there must be a redistribution of heat or energy by both the atmosphere and the ocean towards the poles in order to maintain the heat budget at every latitude. And you can think about a piece of a column in the atmosphere or the ocean. Okay? You have heat getting in. You're supposed to have at the equator you have more heat getting in, and so you will need a meridional transport in this sense, okay? Not considering transport in the zonal direction. So what you get is this picture, I think, yes. Okay, so this is latitude, and this is heat transport. Okay, and this is for the total, the ocean and the atmosphere. This is for the ocean, and this is for the atmosphere. Okay, so the atmosphere transport more heat, okay, because it is mostly done by the eddies, and this is the transport by the ocean meridionally. So it's positive, and here is negative towards the south. So they are always transporting heat towards the poles. In the equatorial regions, actually the meridional heat transport by the ocean is larger than that of the atmosphere. You can divide the heat transport, this is the same thing, you can divide the heat transport of the ocean into the contribution by the different basins. Okay? So black is total, red is the Atlantic, blue is the Pacific, green is the Indian. So the Indian doesn't go farther north than 20 degrees, so it transports heat towards the pole. The Pacific is quite symmetric, as you see. Okay, it's transporting heat to the north and to the south, quite symmetrically. And that is symmetric because it doesn't have a deep circulation. So it's only, the transport is only achieved by the wind-driven gyres that are quasi-symmetric around the equator. So the Pacific is transporting the same amount of heat towards the North Pole than the heat that is transporting towards the South, because the circulation in the Pacific is roughly symmetric. The Atlantic instead is not symmetric at all, and actually if you see, the Atlantic is transporting heat towards the north at all latitudes. And the Atlantic is transporting heat towards the north at all latitudes because of the deep meridional equatorial circulation that is upwelling in the Southern Ocean and is crossing the equator towards the North Pole, where it is sinking again. So the Atlantic is transporting heat to the north at every latitude. Within this red line There is also the wind-driven contribution, which is roughly symmetric. Okay? But the transport by the meridional return circulation is much larger, so that the total is always positive. So the Atlantic is transporting heat from the south, let's say the South Pole to the North Pole, and is the only basin that is doing that because of the deep meridional return circulation. That's why the Atlantic Ocean, in a climatic sense, is so important compared to other basins, right? In terms of redistributing heat meridionally. I'm not going to go into that. So, what was I supposed to say? Well, that's it. You're very worried about the about the beat. Oh, it's quiet. Okay. So I think I'm done. And I will put all the notes on Slack. And these slides, only the part that we talked about of these slides on Slack, okay? The rest, I should clean this up a little bit. Anyway. Do you have any question in general? If you have any question when you're reading the notes, if you have any question, just drop me an email or come to my office or anything, okay? Don't wait the day before the exam to ask for clarifications or something. If I made a mistake on the notes or anything. Okay. And so on Wednesday you will start the third part. That is based on this, so given the circulation that you have seen, the wind-driven circulation, the meridional returning circulation, what is the transport of traces and what is the by all the different circulations. So you will see, I just made a few examples because I know that you will talk about this more in detail, you know, when I talked about carbon-14, oxygen. I just made a few examples, but you will go into more details, basically on how you can trace water masses with traces. In the atmosphere you talk about traces a lot, but also in the ocean you talk about traces. It could be anthropogenic CO2, it could be carbon-14, it could be oxygen. Okay? So how do you trace water masses by these traces, and how do you diffuse or mix those traces between water masses? And that is very important for climate and for climate change. If a water mass in the ocean, for example the North Atlantic, sinks to the bottom and takes with it CO2 or an anomaly in energy or heat, how is that transported, how is that diffused and mixed, and where does it go? Where does it go? It depends on the circulation that you have seen. How it is mixed and how it is diffused depends on small scale and large scale mixing processes that you will see in the third part. Questions? Nothing? All clear? Okay, so have fun with the third part, and then I'll see you at the exam. So we'll have one single exam with 2 or 3 questions for each part. Did you receive notes for the first part? Notes or slides or something? Nothing at all? See, now you have questions.
He said he will have 3 slides, I think, but then his first slides, I don't think any of us received. Not bothering.
Okay, do you want the notes, the slides? Or you don't need to? Do you want me to ask him to give you the notes and the slides? Yes. Okay. I will.
The exam is going to be like at the middle of June or something like that?
When the third part finishes, we can set a date.
Yeah.
When is good for you. I don't know if good for you means as soon as the course finishes or later, so you have time to study, or okay. So you will have to tell me these 2 weeks we are very busy, so can we have the exam later or before? You let me know when it's best for you.